many people are able to actually take some time to try to do the work outside of these lectures.
Yep, I did the bound name and free name definition, and I looked into the definitions of the blue calculus and ambient process calculus, and then I got partway through the linear logic, then sort of stopped there, and I'm looking forward to reading that paper later.
That's awesome. Cool.
And we also went over some of that in discussion, the blue process calculus and the ambient process calculus on Friday.
Oh, good. That's very good. That's excellent. So anyone else? I know Glenn Braun was able to do some work outside of class.
Huge shout out to Jake for kind of organizing outside of his class the Friday, and also last week right after class we had like a 20-30 minute session. So that's the extent that I reviewed outside of class, but it was very helpful.
Good.
I replied to the email Jake sent around with my submission. You were in the recipient list, so I thought you would get it. So I did the row calculus and Scala, also the row calculus grammar in Scala. Yeah, struggled a little bit whether we should put the anamorphism within the within this type system as well, or whether we should implement such a function. Yeah.
Okay. Good. Those are good questions. Let's see. All right. Anyone else? Okay. Well, we need to. We definitely, if we're gonna. So the aim of the class is at the end of this, you guys can design your own calculi. So we really have to get a good understanding. Let's see. I hope Nate is going to join as well. Let's see. I'm just going to send out. Just okay. Just looking for the course list to send out a reminder to join. 1 second here.
Hey Greg, while we wait, did you get the bio to Lilia?
It's on the website.
Okay, I'll text her. We'll sort it out.
Okay, I'll send it. I'll send her a link again. Okay, let me see.
Greg, when you say that our goal, we should be able to design our own calculus at the end of the class, is it something that you see like an explosion of more calculi over the next 25 years, or is it just something that we should be able to do just because we should be able to?
I mean, for sure, people should be aware of the possibility of domain-specific languages. So domain-specific languages are very much an approach to problems. So you can think about a lot of different problems from a language perspective. And this idea goes all the way back. If you there's a very famous uh, book in computer science called "The Structured Interpretation of Computer Programs," and this is by the people who designed Scheme, which is a very well received programming language. And their proposal also is that um, you can solve a lot of problems with little tiny languages that are just tailor made for a particular problem. Whether you're trying to support biologists who are looking at a cell's signaling regime, or looking at a particular call, a domain-specific language can be an appropriate way of tackling the problem. Likewise, if you're looking at an application in the blockchain space, a domain-specific language which captures the range of behaviors of users within the application is a sort of time-honored approach in computer science. So if you understand what makes a calculus tick, then you have at your fingertips one of the most powerful problem-solving methodologies that we've come up with in a long time. So from that point of view, yeah, I fully expect there to be an explosion of calculi, because domain-specific languages are a really, really good way to solve problems. If you can even look at the object-oriented methodology as a kind of if you squint at it, you realize that it's an approach to creating domain-specific languages. The methods that one associates with an object are essentially the utterances in a free grammar. What object-oriented methodology is missing is a clear and concise way to constrain the order that you can call methods. For example, if you have an object that is representing a session with a data resource like a database or some other kind of data resource, then typically you need to initialize the session before you can start making transactions against the session. And then finally, you need to close the session down. Otherwise, the work can get lost. So there's an ordering on those events, and that's something that's missing from the object-oriented design methodology that is put back into place um, with the approach to the design of computational calculi. This design methodology is really much more general than just designing sort of these fundamental models of computation. They can be applied at all levels of the computational, the applications of computation. So let me just stop there and see if people understand what I'm driving at.
Yeah, that's great explanation. Thank you.
Sure. Okay. We'll get started with today's hmm. Okay, so I'll go to screen share, and here we are. Now, we've talked a bit about alpha equivalence, and that was in the larger context of structural equivalence. So how many people feel like they really have yes, that's right. So a lot of the factory patterns and these kinds of things are very much in alignment with the with that sort of thing. Okay, you've got a notion of alpha equivalence under your belt. Yeah, okay, so Jake says yes. Anybody else feel like they understand? They could explain it to someone else. Silence means you don't understand.
I feel like I have an intuition, but I don't think I could teach it to somebody else.
Okay, all right. Let's see. Got it. Okay, all right. So the notion of binder, like we see in the for comprehension for the row calculus or the input process, the input guarded process in the pi calculus, or the abstraction in the lambda calculus, is a really important idea. It's I'll after this in a different way. Let's see if we can do this. So we have this one. So how many people here are familiar with Java or Scala?
Yep.
Okay.
Yes, Java.
Okay. So Zohad, what about yourself? Casper, what about yourself? Are you familiar with either Java or Scala? Roland?
Yes, Java.
Okay, okay. Tom?
I don't have any experience with Java or Scala.
Oh, okay, okay.
I also have a little bit of basic experience with Java, but not very particularly, and also not very much.
Okay, okay. I wonder if there's a programming language we can all use. And so essentially, if we have some method, let's see, we've got a bunch of chats here. Let's see what they say. Okay, Java. Okay. All right. Good. Looks like Java. Now I'm gonna have to dust off my Java syntax. I barely remember. There we go. Okay. So this will probably be Pigeon Java and more Scala than Java. I can barely remember Java anymore. So if I have some class C, and inside I have some method, say M. So so it returns some type t, and then, okay, someone's chatting away here. Okay, cool. Well, so we don't have to have a lot of fancy stuff. So we have some method that returns type t, and we'll call that method m. And let's say that it has some argument a. And let's see, if I recall Java, they put the type on the left rather than on the right. So it takes as input a type a, an argument of type a. Oh, and I think there's no colon in Java. Okay, so then inside the body, we might use a, for example, we might test if some predicate of a, say pred of a, and then we do something, and else we do something, let's do some other thing. Okay, so there's our method. Let me clear off some space here. Okay, so the key idea with alpha equivalence is, and I apologize to repeat this for those who do have it, but it is important that everyone gets this. Okay, the key idea is that if I change this to, say, a B, leave the type alone, but if I change this to a B, then everywhere that A occurs, as long as it's not bound by some inner method, like here, then these two programs are the same. Does that make sense, Tom? These two programs are that we don't want to treat them as different. They're the same. And I think everybody understands this sort of intuitively when they're programming. Does that make sense, Casper?
It's also just understandable from the perspective of like when we're learning algebra, you know, x equals x plus 2 means the same thing as y equals y plus 2.
Yeah, that's exactly right. That's exactly right. So this idea that the exact variable name doesn't matter as long as we're consistent.
Yeah, and the way I think about it, correct me if I'm wrong, the result of running that could be a different answer, but the structure of the computation is the same. Is that right? Because the A and the B are different? Or am I just totally off?
No, the result will be the same. These two programs will behave in all contexts in this as the same program.
Okay.
Yeah, that's kind of the important thing, is that the result is the same.
As long as there's no non-determinism, like so two different runs of like a Rolang process.
Right, that's correct. That's it. But we'll get into exactly what we mean by equivalence in the upcoming lectures, the equivalence of programs. But one way to think about it is that in all contexts, they behave the same. A program is equivalent to another program if they're substitutable in all contexts, which covers this idea of that includes non-determinism.
And so this little a can equal 1 and little b can equal 6, but when you run the program,
No. When little a equals 1, little b equals 1.
Okay.
So that's the important thing, is that the variable name doesn't matter as long as we're consistent with its usage.
For me, I think when you compile it, you're going to create a memory location for this variable, and the name is kind of out of the picture.
Mm-hmm. That's
So
another way of thinking.
It creates a slot for memory, and then whatever gets stored there is at runtime.
Yeah, exactly. So you can also, like in the lambda calculus and in programs that are informed by the lambda calculus, there's something called the de Bruijn indices. And that gives you a way of giving something that's more abstract than a memory location, but has the same effect, that variables are compiled down to the same de Bruijn index. And basically what that does is that's counting the nesting level in the level of abstractions. So if we look here in lambda x dot m, that's sort of the inside m, that's the first nesting level, right? And then if you had another lambda inside that, that would be the second nesting level. So you can count your nesting levels, and you can do some other things to make sure that you don't get name collisions, and that will give you a more abstract way than memory locations to recognize that the variables can the difference in the name of the variable gets erased, and it's really just the abstraction sites that are important, the sites and the terms and what they're expecting relative to inputs. Okay, so hopefully people can chew on this. Go ahead.
One question, should we think of it that you bind the new variable, and so you substitute the old variable in the sense of A substitutes B, or it is also somehow permitted to think that you substitute every B with the content, that means with the number 3 or something like that?
The former is going to be there's a way to make sense of your latter statement, but the former is sort of going to lead you more in the right direction. Yeah, if you think in terms of substitution, that's a really good way to think for these kinds of things. Okay, so hopefully people will take some time to digest this if you haven't completely digested it.
So I just had another wacky way to think of it, Greg.
Yeah.
Imagine a recipe for like cookies or a cake. That recipe could be in German, English, Japanese, so on and so forth. But it's the same recipe for so different names for the ingredients, but exactly the same product.
Yeah, that's correct. That's a nice way of thinking about it. I like that a lot. Good. It's also very interesting if people want to take a look at it. There's a variable free calculus called the SKI calculus, and there you can compile all lambda terms down to SKI, and that gets rid of variables in another way. And you can kind of see the action of abstraction in terms of this SKI calculus. So if you're interested in taking a look at it, it's good to look at it both concretely and abstractly, sort of at the same time. And if you flip back and forth between the concrete and the abstract, step by step, you can get closer and closer to the intuitions that are going on here. At a higher level, in terms of the design of computational calculi, it's important to understand that alpha equivalence isn't the only kind of equivalence. So as I mentioned, here we also, in the row calculus and in the pi calculus, we have some other equivalences, right? So the par operator provides us with another set of equivalences. If you think about this from the point of view of abstract algebra or universal algebra, what we are saying is that the par operator, together with the collection of processes or programs in the row calculus, forms a commutative monoid. And so for those people who are familiar with the algebraic structures, a monoid is well, in the ordinary presentations, a monoid is a set together with a binary operator that satisfies certain equations. In particular, there's a special element called the identity, that when you combine that with the binary operator, using the binary operator with any other element, it always returns the other element. So that's what the zero does here in this expression. And then similarly, the operation needs to be associative. So if you parenthesize the combination of three terms this way, or you parenthesize the combination of three terms this way, they must give you the same result. If you look at the lambda calculus and the application operator, that's not associative. So we don't insist upon this rule for the lambda calculus. Instead, we adopt a convention which says we associate to the left. That's the approach of the sort of traditional lambda calculus, and something that's adopted in Haskell and things like that. And then in the case of par, we add an additional equation, which has to do, so this is not just a monoid. So these are the two monoid equations, but we also erase the order that we write them down. We forget about the order that we've written them down, which represents our intuitions about things running in parallel. So this rule, which allows you to put them on either side of the vertical bar, that's commutativity. So for the par operator in the row calculus, and as well as in the pi calculus, we have a commutative monoid. So, but if you want to step back and even further, and it's important to have this level of abstraction if ultimately we want to understand Ladle and the Ladle algorithm. The grammars of the computational calculi are algebras, or are representable by monads in almost every case. In most of the sort of computational calculi that we're talking about, they're representable by monads or combinations of monads. The one place where you have to be a little careful is when you do introduce variables like lambda abstraction, or the four comprehensions, or the new construction in the pi calculus. And there is a treatment of this separately. And if you remember, I mentioned Jamie Gabai's work on nominal calculi and nominal theories. So there, essentially, Pitts and Gabai have found some monadic machinery that abstracts out the sort of the variable machinery. So then, the relationship between the grammar style presentation and the monadic presentation was identified by a mathematician like, oh my gosh, 50 years ago now, Bill Levere, who showed that um, this grammatical style presentation that can be captured in what's called the Levere theory. So you can essentially identify Levere theories with the grammars that we presented. And then Bill Levere showed that all those theories have a correspondence to a monad. So you can always, there's an isomorphism. So you can either start with the monad and then get the theory, or you can start with the theory and get the monad. And that's important because when we're going to talk about being able to generate type systems, the monad is going to represent a key ingredient in the type system. Now the other piece of the puzzle where this is the structural equivalence. So we can think about a wide variety of monads as essentially giving us the freely generated something or other. So that's a lot like the language generated from the grammar. So the language, the set of all possible legal expressions from the grammar is our language of the grammar, and then the free monad is like that. Those two notions are essentially the same. But then where do these structural equivalences come in? How does that fit into the categorical presentation? And those turn out to be the algebras of monads. So we can't, unfortunately, we can't get too deep into the category theory without making this course about twice as long. But if you do get into the category theory, what you'll see is that there's associated to every monad is a collection of additional structures which introduce these kinds of equations, like we're seeing here in front of us. So, for example, you can freely generate the set of all strings over over an alphabet. Okay, so if I have the alphabet A and B, then I can consider all finite length strings involving A and B, including the empty string. And then concatenation, so just placing two strings next to each other, is our binary operator. So if I have the string A and I have the string B, then I can combine them into the string AB. If I have the string AB and I have the string BA, I can combine them into the string ABBA. Now, in this case, the empty string that has nothing in it at all, if I concatenate any string with the empty string, I always get the initial string back. So the empty string forms our identity. And we can see that if I concatenate a string S with another string and then a third string, it doesn't matter the order that I have concatenated them. So just the set of all strings freely generated, if I interpret it as a monoid, then that I introduce these additional equations, and that gives us our algebra, which is sort of this extra level of structure that we recognize beyond just the set of all strings freely generated in this way.
Can you extend that example at all if it makes sense that, like, say that a forward string and a reverse string we considered structurally equivalent, what would how would we sort of define that relationship in terms of our monads?
You could the forward string and the reverse string might be a little bit more complicated, but you could certainly do groups, right? Where you have you could insist that for every letter in the alphabet, we have a corresponding additional letter, say, where we put a bar over the top of the letter. So if we have A, then we have A bar. If we have B, we have B bar, right? And then we would have a rule that says that when two letters that are the same except for the bar, one is a bar of the other. And we would have to include, yeah. So we'll go one step at a time. So if I put A next to A bar, then that evaporates into the empty string. And if I put B next to B bar, that evaporates to the empty string, and so on. And then we also we want to close it so that if I bar an A bar, I get back to A. And that gives you a group. And so that's another algebra that we can place over the set of all free strings, the freely generated strings from an alphabet. So yes, it does extend, and that's the heart of the Lever's observation, that all of the sort of standard algebraic theories can be captured in this way. And in some sense, sort of you can build upon that by, well, we'll get into later. But this is the sort of general setting where we might talk about structural equivalence. And it's important to see that sort of very broad picture, because as I mentioned before, language design is a viable and important approach to problem solving for applications. It's design. Thinking about a problem as a language design problem would dramatically improve user interface design, for example. So that's why it's important to be able to have the facility to go back and forth across all these different domains. And the other piece of it is that it allows you to reuse design patterns from one domain to another. Let me give you just a simple example. If you think about, since we're on the topic of user interface design, if you think about the interaction with a mouse, right? So if I click and I start moving the mouse, hopefully everyone can see that. And so that's exactly the same as a session, right? So we talked about a session resource where I have to initialize the session to a particular data resource. And then I accept some number of transactions, and then I close the session that releases the resource. Well, watch. Clicking initializes the session, and then moving the mouse is all of the transactions associated with the session, and then releasing the mouse is releasing the resource and closing the session. So those two design patterns are the same. And when I think about them in a language theoretic point of view, then I can see that it's I can not only intuitively understand that it's the same design pattern. But when I write down the design patterns as languages, they are literally the same. So my code starts to have a much broader range of applicability. I get more bang for buck in terms of the code I write. And that's why this kind of stuff is important. Okay, so hopefully that made some sense. So we have just a few minutes, and now I really want to turn our attention to the final piece of the puzzle. The final piece of the puzzle is what's called operational semantics. And this is what distinguishes this element of computer science from classical mathematics. So we talked about a couple of classical mathematical structures, monoids and groups. And in monoids and groups, we only have the freely generated structure and the structural equivalence. So the freely generated structure and the structural equivalence are how do I say this? So the structural equivalence, those equations go both ways. So if we look back here for a second, I can always run this equation in either direction. I can run this equation in either direction, right? So the information on both sides is the same. And that's very, very important, because there's no forgetting. There's no forgetting of information from one side to the other. Now, the equation itself might say something about the loss of information. So, for example, this equation erases order. And this equation erases history. So if you think about the history of forming the term, like the sequence in which you form the tree that is the term, this erases that history. And this erases the sort of linear order. But that's everything that appears on the left-hand side of this equation appears on the right-hand side of this equation in terms of terms. Everything that appears, if we forget about the parens for a minute, everything that appears on, every term that appears on this side of the equation appears on this side of the equation. So the total amount of information remains the same. When we move to operational semantics, we lose structure. We forget things. We forget term structure. So these are these rules are unidirectional. They're not bidirectional. So in the case of application in the lambda calculus, when we apply an abstraction to another lambda term, then it reduces in one step, rewriting m by placing n in every place where x was. Every occurrence of x that was bound by this lambda is replaced by n inside m. So we get a new term. A similar thing happens in the row calculus. But the rewrite rules are a little bit more sophisticated. So we'll go over those in detail. So here you can think of this for comprehension as very much like an abstraction, except that instead of having to be textually next to each other in order to run the reduction rule, we give a name to the site where they might be next to each other. So that's what the X is. So instead of having them to be syntactically next to each other, we name this place where they become next to each other and call it X. And whenever a process that's waiting for input, i.e. is an abstraction, is located at X, and there's another process which is providing output, and that's located at X, then we reduce and we take the code for Q and we put that in place of Y everywhere it occurs inside P, bound by this for comprehension. So let me just stop there and make sure that everyone is kind of following along what I'm saying.
Yeah, I'm almost there, Greg. So I can see how P is a context for which you're doing the substitution, and I can see where, but the location parts, I'm almost there. But could you go over the sort of how X is a description? Is it a description of where something might be?
So you can go at this in two ways. You can either just you can look at this textually, and you can say, whenever I have a for comprehension with a vertical bar, and the for comprehension has got an X in the right hand side of this arrow, and there's a vertical bar, and there's an output, and that output is also at the same X. Then we do this. Now notice that because we have this other rule up here, so let's run this for a bit. Let's run one of these. All right, so suppose that I have for Y. Let me go grab that. Oh, I've got it here, I think. Is it this? No, that's not it. Sorry. Just want to grab that left pointing arrow there. Got it. Okay. All right. So whenever I have I'm looking for a Y coming out of an X, and then let's say that I have an R and an S and a T in between, and then I've got output of Q at X. Okay. So with this setup, just looking at it entirely textually, I can't run this rule, can I? Because they're not right next to each other. But I have this rule here. So the next thing I can do is I can swap this one and this one. So let's just do that. So we'll grab this one and we'll put it on this side of T. Right? I'm allowed to do that. Okay, so I still can't run this rule, but I can swap this one and this one. And I think you can get the pattern, right? You see where I'm going. So I'll grab this one. I'll put it here. Right? And likewise, I can swap them again. And now these two are right next to each other. So now I can apply this, but notice that this doesn't mention any other context. There's no other processes running in parallel. So it seems like I'm stuck. It seems like I can't go any further. The next rule tells me how I can go further. It says that if P could reduce to P prime on its own, then P in parallel with Q could reduce to P prime in parallel with Q. In other words, the Q stays the same and just the P part reduces. So now if we go to our example, I get to treat all of this here by the rules of the formation of the row calculus as one process, right? So I'll just call that. So for purposes of discussion, let's just say, we'll say let capital U be equal to all this stuff here. Okay, so now my equation becomes, or my candidate for reduction, I can now rewrite that as U, like this in parallel with U. And now if we go back to our rule, what does it say? Well, it says I can factor this part away and just look at this. So we get to ignore the U, right? And just look at what is to the left of the U, and well, lo and behold, this thing matches our rule. It matches this exactly textually. Does that make sense, Kenny?
Yeah. And so, but the second rule is how that you were able to
ignore the Q, ignore the U part. Yeah.
Yeah, which is important because you wouldn't be able to get there unless you had that notion as well.
That's exactly right.
And these reduction rules are comprehensive to reduction to give you all the possible ways in which reduction is possible.
That's right. That's right. So then this would allow us to rewrite, and it
Sorry,
would,
one question.
yes.
Doesn't U follow from the associative rule?
Mm-hmm.
Only, and not from this other rule that you showed, because I can do the brackets and say this is one thing. RST is one thing, it's U, because of the associative rule.
So yes, but you still need, even the important thing is that you're stuck if you have a U, okay? You can't go any further if you just have this rule here, because you've got this rule doesn't mention anything on the side, right? You have to have exactly and only this. But in our example, we have more, right? Whether you name it U or you leave it unpacked as RST, you still have this extra stuff, and you can't apply the reduction rule. Sorry, you can't apply the reduction rule to the reduction candidate. So you have to have this extra rule here to enable you to do that. Does that make sense?
Yes, thank you.
Sure. Okay, but now there's some. This is bugging me. There's some. Oh, I see what I see what I did. Let me just fix this up. There. Okay. Now Another important part of operational semantics is notice that these two rules are implications. So there's two kinds of arrows mentioned. One is some hypotheses about the processes, and then using those hypotheses, we can then talk about reduction. Whereas in this rule, there's no hypotheses. It's the ground. These are recursive rules. And they're recursive because we assume something about the reduction in order to get another reduction. So here we're saying that P reduces to P prime is our hypothesis. We need that information in order to get this reduction. So if you always needed information about reduction in order to get reduction, you'd never get off the ground. You'd have a bottomless recursion, and you wouldn't be able to make progress to apply your reduction rule. This is where everything stops. This is the workhorse of the row calculus, and there's an equivalent workhorse for the pi calculus. And that workhorse is remarkably like abstraction. They're almost identical, except that instead of having to be textually next to each other, we locate them at this x. And now, Kenny, hopefully you understand that this site is, so when you put things in par, it's like they're freely mixing around. You could think of them as like in a soup, a chemical soup. They're all mixing around. And when they come next to each other, they only get to reduce if they have the same site. Right? If I change this to an x prime here, that process would be stuck unless there was some reduction going on in R, S, or T. So the x is representing this location where they literally can come next to each other, and we can run the application. In this example, or in this rule, you'll notice that this really does make the row calculus a lot like the lambda calculus, because we're substituting in all the information contained in Q for Y. Unlike pi, where we can only substitute names for names.
Yeah, Greg, this is to say these are application specific, or you can use these things to solve real world problems by domain. This seems remarkably similar to you could model something like a chemical reaction like this. So if you have this soup of things going on, and as soon as two things come into one particular configuration, then it's like a catalyst. Then more things sort of happen, and structure kind of comes out of that.
And you're so spot on that several people, including Bill Silverman and Regev Aviv and Hudi Shapiro, built chemical modeling of chemical equations using the pi calculus, using a stochastic version of the pi calculus, and you can associate reaction rates to the channels, and you can get exact models of chemical behavior, and then you can build on that and get exact models of organic chemistry and biochemistry, and then you can get exact models of biological phenomena using the same sets of intuitions that you just had. And that so exact, for example, that my colleague Corrado Priami modeled using this approach, the inflammation process in multiple sclerosis, where the leukocyte begins rolling and tethering along the cell wall. And that's what causes the inflammation. And his models were so accurate that that you could use them to make predictions about the physical phenomena. And those predictions were not predicted by the differential equation, the similar differential equation models of those systems. And those predictions were then verified in the lab. So,
what was his name?
Corrado Priami. He is the head of the Trento Research Institute in Trento, Italy, that has been investigating for the last 15 years the application of process algebraic techniques for the modeling of biological phenomena. So with that, it's Casper time. So I'm going to let you folks go, and next week we'll be able to move on a bit.
Before we go, Greg, what would you suggest as the work we do for this week?
So I would strongly encourage you to take your the work that you've done so far and go ahead and model the reduction rules of the lambda and the row calculus in your Scala or Haskell representations.
Right. Thank you.